Hi, welcome to Atomic Structure Review Part 2. My name is Dr. English. Today we're going to be talking about how we apply concepts of atomic structure to different scenarios. So taking what we learned in the first part of review and applying it to this part. So specifically, we're going to look at the concepts of ground state, excited state, isotope review, how to calculate average atomic mass, and a little bit of practice at the end. So let's first start off by talking about ground state versus excited state of an atom of sodium. So what is the ground state electron configuration of a sodium atom? If you look on your reference table, on your periodic table, you'll see 281. When you look for the symbol of sodium, now you might say, well, where is that? That's in group 1, and here's my symbol of sodium right here, my atomic mass listed up at the top, my atomic number, which is 11, my overall charge, which we'll talk about later, and finally, here is that electron configuration right here. So we can look at this and basically say that we're starting at the lowest possible energy level, which is 2, then going to 8, then going to 1. So my ground state electron configuration will always be what is listed on the periodic table. Now let's look at some possible excited state electron configuration of a sodium atom. So we could have 272 or 182. Are there other possible configurations? Of course there are. So here's what I look for when I'm grading this particular question. I know that the electron configuration of an atom is basically the number of electrons have to equal the number of protons because, again, we're dealing with an atom. I look at here and I see that the atomic number is 11, which means my number of electrons, because I'm dealing with an atom, also has to equal 11. So 2 plus 8 plus 1 will ultimately give me 11. When I'm looking at these excited state electron configurations, I also want to see a total of 11 electrons here. Now, electrons are going to jump from lower energy levels to higher energy levels. So if we look at this situation right here and compare it to our ground state, we could say, well, an electron from the second jumped up to the third. Or in this one down here, an electron from the first energy level jumped up to the third. Ultimately, what I'm looking for is when I add these possible electron configurations together, that I'm still getting 11. So 2 plus 7 is 9 plus 2, that gives me 11. 1 plus 8 is 9 plus 2 will also give me 11. I'm also looking to make sure that we don't violate the maximum number of electrons per shell. So for this one, this is going to be 2, that's maxed out. 7 is below that number, 2 is below that number, so I'm okay there. In this electron configuration here, I have 1, 8, 2. I haven't maxed out any of those electron configurations. So in other words, I'm not seeing a 9 here. I don't want a 9 there. I know that the maximum number of electrons that can be in this second shell is 8. So I can't write an electron configuration that says something like 1, 9, 1. Even though that does add up to 11, it's not going to follow that maximum number of electrons per shell. Now let's talk about understanding energy in excited versus ground state. So let's ask ourselves a question. What occurs when an electron in a sodium atom moves from a lower energy level, in other words, ground state, to a higher energy level, in other words, excited state? Basically, a couple of things are going to happen. First, an electron is going to absorb energy in the form of heat, light, or electricity. It moves temporarily to a higher energy level, but this is a very unstable condition for the electron. So here are two ground state electron configurations for aluminum. So if I wanted to say, all right, let's excite an electron from ground state and push it up to excited state, maybe I take an electron from the first shell and move it up to the third shell. Or maybe I'd take an electron from the second shell and I'd move that one up to the third shell. So basically, when you excite an electron, you're going to move it from its low energy state farther away from the nucleus up to a higher energy state. Now, let's talk about the opposite direction. What occurs when an electron in a sodium atom returns from a higher energy level, the excited state, back down to a lower energy level or ground state? What's happening when that electron goes from the excited state back down to ground state? Again, a couple of things are going to happen. An electron releases or emits, which is a good vocabulary word to know, energy equal to the amount that was absorbed. So the amount of energy that I put in to excite that electron is now going to be released as it goes back down to ground state. The energy emitted can be in different forms. It can be in infrared, ultraviolet, or visible light. Such energy is composed of multiple wavelengths that can be observed as different lines as seen in a line spectrum. Remember, each element has its own distinct line spectrum, almost like a fingerprint that identifies that particular element. Now let's talk about isotopes. What is an isotope? Any of two or more forms of a chemical element that have the same number of protons in the nucleus, in other words, the same atomic number, but having different numbers of neutrons in the nucleus. So let's look at 3 isotopes of oxygen. I know they're all oxygen because they all have the same symbol here, but their mass numbers, 16, 17, and 18, are all different. So these are definitely isotopes of each other. What do these isotopes have in common? The number of protons, because I know that oxygen has 8 protons, because if we look at oxygen on our periodic table, the atomic number is 8. So what is the difference between isotopes? Well, that would be the number of neutrons. So if I have oxygen 16, I have oxygen 17, and I have oxygen 18. For protons here, they're all going to have 8 protons, because if I change the number of protons, I change the element. But in terms of neutrons, because I know that this atomic number right here is made of protons plus neutrons, for neutrons over here, this has to be 8, because 8 plus 8 gives me 16. This has to be 9, because 9 plus 8 will give me 17. And this has to be 10, because 10 plus 8 gives me 18. So again, with isotopes, they'll have the same number of protons, but different number of neutrons. Now let's talk about calculating average atomic mass. And this is a really good skill to go over, because this particular formula is not on your reference tables, so you really need to know how to do this. A moon sample was analyzed in a lab. The carbon in the sample was found to be 97.78% carbon-12 and 2.22% carbon-13. According to this data, what is the atomic mass of the carbon? So the way that you're going to approach this is basically write each percentage times the mass that is given, and then add that to another percentage times the mass that is given for that one, and so on and so forth, depending on how many different types of isotopes are listed. So there's 2 ways to approach this problem, and it really depends on your comfort with working with decimals. So if I was to look at this, I'd say, all right, 97.78% carbon-12. I'm going to turn this percentage into a decimal. So I'm going to say this is 0.9778 times the mass that is listed, plus the second percentage. So I know I need to move that over 2 decimal places. So 0.0222 times its mass. And then I'm going to calculate a number. Done. The other approach that you can do here is say, you know what, I always screw up these percentages. I'm just going to leave the percentage as is, and I'm going to do a different approach. So in that case, you could say, all right, 97.78% times the associated mass, which is 12, plus 2.22% times its associated mass, which is 13, and divide that all by 100. No matter what, you're going to get the same answer here. It really depends on your comfort level with decimals. So if I do 0.9778 times 12 plus 0.0222 times 13, my average atomic mass for this will be around 12.02 grams. Same thing over here. If I do 97.78 times 12, 2.22 times 13, and divide it all by 100, I will also get roughly 12.02 grams. The average atomic masses are the same, just 2 different approaches that you can take when calculating this number. Let's see what you can do. I want you to read through this question, write out your formula, plug in your numbers, see how you do, and then come back and compare your results at the end. Welcome back. Let's see how you did. Magnesium is composed of 3 existing isotopes. Magnesium 24 has a percent abundance of 78.99%, magnesium 25 has a percent abundance of 10%, and magnesium 26, because this elevated 26 right here is just the mass number, has a percent abundance of 11.01%. Calculate the average atomic mass of magnesium. Okay, I have 3 different isotopes that are involved here, and I want to make sure that I list all 3. So let's start with the first one. Magnesium 24 has a percent abundance of 78.99%. So I like just to convert my percentages into decimals. So I'm going to do 0.7899 times 24. I'm going to add that to magnesium 25 has a percent abundance of 10%. So 0.10 times 25 plus, and then magnesium 26, because again that's an atomic mass, has a percent abundance of 11.01%. So I'm going to again change that percentage into a decimal like this, multiply it by 26, and if you're originally doing this with a graphing calculator, which you will not be using a graphing calculator on the Regents exam because you're not allowed to, you just have to be really careful about how you plug things in and making sure you put brackets in the right place. If you work these out by saying, okay, I'm just going to multiply this together, get an answer, multiply this together, get an answer, multiply this together, get an answer, and add them all together at the end, could be a much safer thing to do. So if I work this out, my answer to this question will be 24.3 grams. So hopefully your answer and mine are about the same. So what did we learn in this tutorial? We went over the concept of ground state. We went over the concept of excited state. We did a little review of isotopes. We talked about how to calculate average atomic mass, and then we did a little bit of practice at the end. Need more help? Feel free to contact me. Have a great day.